So hello, and thank you for the opportunity to introduce you to the North Atlantic Oscillation, or the NAO, and the Pacific North American Pattern, or the PNA. My name is Nat Johnson, and I'm a meteorologist at the NOAA Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. If you are listening to a recording, I apologize that circumstances did not allow me to present this lecture live, but I'm grateful for this opportunity nonetheless. The NAO and PNA are the two dominant Northern Hemisphere atmospheric teleconnection patterns, and they have far-reaching impacts throughout the hemisphere, so they are worthwhile teleconnections patterns to understand. So these are the topics I plan to cover during this lecture. I'm going to start with a little history lesson about these two teleconnection patterns, showing that the NAO in particular has been recognized for centuries. Then we'll get a more modern perspective on the NAO and PNA patterns, time series, and impacts. And then finally, we're going to focus on the predictability of the NAO and PNA from subseasonal to seasonal timescales. So let's start with a little bit of history. So first, we will note that atmospheric teleconnection patterns, and particularly the NAO, have been recognized for centuries. And one of the earliest examples that illustrates this is from the Norse, or Viking settlers, who arrived in Greenland around the year 985. And the Norse, who appeared to be very interested observers of the weather, also seemed to be aware of teleconnection patterns in the North Atlantic Basin. And so there was an anonymous Norwegian book dated back to the year approximately 1230 entitled The King's Mirror. And this book, in the form of a discussion between father and son, hinted at the existence of one of the dominant teleconnection patterns, the North Atlantic Oscillation, or NAO, by noting that severe weather in Greenland coincides with warmer weather at distant locations, and vice versa. And a very similar idea was expressed in The History of Greenland, which was written by David Krantz in 1767. And in this book, the author wrote, "It has been many times remarked that the weather in Greenland is just the reverse of that in Europe, so that when the temperate climates are incommoded with a very hard winter, it is here uncommonly mild, and vice versa." If we look at a more modern perspective of this NAO, we see observations that really agree with this passage that came a few centuries earlier. So we have two phases of the NAO. So in the negative phase, which is depicted on the left here, we can see we have warm conditions throughout a large portion of the Arctic, including Greenland, that coincide with much cooler conditions over Europe. And then in the positive phase of the NAO, it's just the opposite. So cooler than average conditions over Greenland and parts of the Arctic coincide with warmer conditions over Europe. So a clear example that this is an idea that was known by settlers even before we officially had a teleconnection patterns defined. So it wasn't until the 20th century that we saw a more systematic study of atmospheric teleconnection patterns, particularly with the pioneering work of Sir Gilbert Walker in the 1920s. So Walker in 1924 used correlation analysis to find the dominant teleconnection patterns, including the NAO and the so-called North Pacific Oscillation. And then after a bit of a lull, a renaissance in teleconnection pattern research ensued after 1960, particularly when Van Loon and Rogers in 1978 confirmed many of the earlier results of Walker regarding the NAO and the North Pacific Oscillation. Then there was a landmark study of Wallace and Gutzler in 1981 that provided a comprehensive summary of Northern Hemisphere teleconnection patterns, including the NAO and the Pacific North American Pattern, or PNA. And this was the first study that I'm aware of that used this term, the Pacific North American Pattern, or PNA. So while earlier studies recognized that there were coherent variations of weather and climate over the North Pacific, as noted above, I believe that the PNA wasn't officially recognized as one of the dominant teleconnection patterns until this Wallace and Gutzler study. So let's get a more modern perspective on these two teleconnection patterns, starting with the NAO. So what is the NAO in a little bit more detail? So the NAO is one of the dominant Northern Hemisphere atmospheric teleconnection patterns, characterized by coherent fluctuations in atmospheric mass between Iceland, Greenland, and the Azores region. And so as I mentioned earlier, we have two phases of the NAO. So in the negative phase of the NAO, which is depicted here on the left, we have an unusually weak Icelandic low and a stronger than average Azores high. And oftentimes this sort of configuration coincides with blocking over the North Atlantic, and we tend to have warmer conditions, as I mentioned, near Greenland and also southern Europe, but colder and drier conditions over northern Europe and parts of the eastern US. So during the positive phase, depicted here on the right, we have a stronger than average Icelandic low, and we have a northward and strengthened jet stream that really effectively steers systems into northern Europe, so it tends to be warmer and wetter over northern Europe, whereas it's cooler and drier to the south. So the NAO pattern is strongest in winter, but it's present throughout the year. And it is closely tied to the more hemispheric Arctic oscillation, the AO, or the Northern Annular Mode, NAM, and we'll talk a little bit more about that in a couple of slides. So as I mentioned, we have two phases of the NAO. And so here we are looking at the pattern from a sea level pressure or a geopotential height anomaly perspective. And whether we look at it at the surface, at the sea level pressure, or whether we're looking at geopotential heights in the mid-troposphere or upper troposphere, we see a very similar pattern. And that's because the NAO is an approximately equivalent barotropic pattern, which means it's basically vertically stacked. From sea level pressure to the mid and upper troposphere, it's a very similar looking pattern. And here we're depicting the NAO in the positive phase. So the blue contours represent negative sea level pressure or geopotential height anomalies. The red contours are positive sea level pressure or geopotential height anomalies. So we can see during the positive phase, we have that stronger than average Icelandic low. These are the blue contours over the North Atlantic region. And a stronger than average Azores high, and really this belt of anomalously high pressure extends all the way from eastern North America through southern Europe. And we can superimpose this on the climatological geopotential height field. And so this is the NAO, the negative phase of the NAO on the left, the positive phase on the NAO on the right, with the climatological geopotential height superimposed. So first of all, notice for the negative phase of the NAO, we see these the gradient over the North Atlantic is much weaker. So the jet is weaker, and we see oftentimes, as I mentioned, blocking over the North Atlantic. So very restricted flow. That trough over the eastern North America and over Europe is deepened. That's why we get these tend to have these colder conditions there. Whereas during the positive phase of the NAO, we see an enhanced meridional gradient of the geopotential height, which is associated with a stronger and northward shift of the jet. Very fast-moving systems that bring warm and wet conditions to northern Europe. And so as I mentioned a couple slides ago, there's been some debate about whether this more regionally confined NAO paradigm is more appropriate than the more annular Arctic oscillation, or AO, paradigm, also known as the Northern Annular Mode, as a counterpart to the Southern Hemisphere Southern Annular Mode. And back when I was a graduate student, I know there was considerable debate about whether this AO pattern really is a distinct pattern from the NAO. So if we compare the two patterns, so that over the North Atlantic, the AO pattern is very similar to the NAO pattern. We have this dipole around the Icelandic low region and the Azores high, but the AO has a more of an Arctic extension of this anomaly near Iceland. We also see this positive anomaly near the Aleutian region. And so it does have a more annular appearance, where we have anomalies of a single sign over the Arctic, and then positive anomalies, opposite sign anomalies in the mid-latitude belt around it. And I won't get into the debate too much. I'll just note that the patterns are strongly related. So if we look at time series of the AO or time series of the NAO, they are highly correlated. In fact, my former mentor, Stephen Feldstein, wrote a study back in, I think, the mid-2000s, basically determining that the AO and the NAO are statistically indistinguishable. So the take-home point here is that the lessons that we learned about the NAO in today's lecture generally also apply to this AO, or northern annular moat pattern. So as I mentioned, NAO variability is strongest in winter, but the pattern persists throughout the year. And so here I'm showing just the NAO pattern at 4 different calendar months. This is taken from the NOAA CPC website, so they define the NAO for each calendar month, and this is just a representative of the seasonal cycle of the NAO. So the pattern is most mature and strongest in the winter. So look at the January pattern. We see the strongest anomalies, and we see this classic NAO dipole pattern. In April, we still see this pattern. It's a little bit weaker. Then by July, you can see it's notably weaker. So the anomaly near Greenland stays pretty much spatially fixed throughout the year. But notice that the Azores high anomaly starts to shift a bit northward during the warmer months. Then here we have it in October, again weaker than in the wintertime. But overall, it's a pattern that does persist throughout the year and does have impacts on the climate, just as they're more pronounced in boreal winter. So how do we define the NAO pattern and its corresponding time series? Well, there are many ways to define an NAO index, but perhaps the simplest is the so-called station-based NAO index, which is just the difference of normalized sea level pressure between 2 stations, one in Lisbon, Portugal, and the other in Reykjavik, Iceland. And what I'm showing here on the left, this is the station-based NAO index going all the way back through 1865, and this is a winter mean, December through March. So you can see the fluctuations, from the negative to positive phase, with a strong interannual, some interdecadal variability superimposed. And we already see one of the key strengths is that this record goes all the way back into the mid-19th century. So we do have observations at these 2 locations going back into this time period. So it's rare to have such a long continuous data set just based on observations. And the second strength is it's very simple to construct and easy to understand. And it also happens to be highly correlated with other more sophisticated measures of the NAO index. However, there are a couple of disadvantages as well. So as we mentioned, it's only based on 2 fixed locations, so it does not allow the evolution of the NAO spatial pattern across different timescales. So we've already seen that the NAO evolves throughout the calendar year, so it's not a fixed pattern, but it has a pattern that evolves from winter to spring to summer to fall. But it also can evolve on these the multi-decadal timescales. So the NAO pattern in a certain multi-decadal epoch may be slightly different from the NAO pattern in another multi-decadal epoch. And so an index that's just based on 2 fixed locations will not capture these variations. And the second disadvantage is that we have more noise from short-term weather variability when you're only considering these 2 locations. So we know that there may be synoptic scale storms that impact the sea level pressure at Lisbon, Portugal, or Reykjavik, Iceland. And these synoptic scale variations may not reflect the larger scale and the lower frequency variability that's characteristic of the NAO. But despite these 2 disadvantages, it's still a simple and effective way to define an NAO index. So moving on to some more sophisticated ways to define the NAO pattern and its corresponding time series. I'd say most current research and operational applications define the NAO pattern and index through empirical orthogonal function, or EOF analysis of sea level pressure or geopotential height anomalies. And so I believe you already had a lecture on statistical techniques to study teleconnections and how to define climate indices. So this topic may have been covered already, so I'm not going to go into depth here, but I'm just going to give just a very brief summary of EOF analysis and how it's applied to the NAO and other teleconnection patterns. So EOF analysis decomposes a large data set into a smaller set of patterns and associated time series. And so these EOFs are eigenvectors of an anomaly covariance or correlation matrix of a spatially weighted field, such as sea level pressure or geopotential height anomalies. And the leading EOF is the linear combination of original variables, which in this case correspond to gridded sea level pressure or geopotential height, that maximizes the amount of explained data set variance. So again, we have a set of variables which are gridded sea level pressure or geopotential height, and this leading EOF is the linear combination that gives us a single variable that can maximize the amount of variance of the original data set variance. And then the second EOF explains the second most amount of variance under the constraint of being orthogonal to the first, and the third explains the third most amount of variance, again with that orthogonality constraint, etc. And so then these EOFs are sometimes rotated in space, including for the study of the NAO to improve physical interpretability. So there are different ways we can spatially rotate these EOFs. A lot of times there's an orthogonal rotation, and usually it's a method called Varimax that's applied. And when you rotate these EOFs, they tend to be more regionally confined and simpler to interpret, simpler to understand from a physical standpoint. And EOF analysis in the climate sciences, it's sometimes called principal component analysis. So these these terms are often used interchangeably. So the NOAA CPC uses this rotated EOF analysis to define their teleconnection patterns in time series. And because many users download the CPC indices, I think it's good to have an idea of how the NAO and other teleconnection pattern indices are created. And so they use a method that's adapted from a very famous study by Marston and Livesey in 1987. So first they do an EOF analysis of the monthly mean standardized 500 hectopascal height anomalies in the northern hemisphere poleward of 20 degrees north. And then for each calendar month, they calculate the 10 leading EOFs, which are then rotated. They use, again, this Varimax rotation. And I note here that if you just did the leading unrotated EOF of northern hemisphere winter 500 millibar height anomalies, you tend to get the Arctic oscillation pattern. So without rotation, you get the less regionally confined and more annular Arctic oscillation pattern. So anyhow, we have these 12 sets of rotated EOFs, which provide the 10 dominant northern hemisphere teleconnections. And the NAO generally emerges as the leading pattern, so the pattern that explains the most amount of variance among these rotated EOFs. And these monthly teleconnection patterns are linearly interpolated to each calendar day. So there's an evolution throughout the entire calendar year. And to get the indices, so this is where the CPC differs from other techniques. So they calculate, the indices are calculated through a least squares regression. So indices are the solution to the system of equations that explain the most spatial variance of the observed standardized height anomaly field in that day or month. And this differs from what we often see in the research, where the indices are simply the principal component time series, so the projections of the data onto these rotated EOF patterns. So here they're using a least squares regression to get the indices. But overall, there are different, as I mentioned, different ways that you can get the indices, and usually they're highly correlated with whatever method you use. So we've already talked a bit about the impacts of the NAO, and here I'm just going to reiterate some of the winter impacts of the NAO in the positive phase. So again, in the positive phase, we have below average sea level pressure over the North Atlantic, the Iceland region, Greenland, above average sea level pressure in the belt across the North Atlantic into southern Europe. And associated with this positive phase of the NAO, we have above average temperatures over much of northern Eurasia, eastern US, below average temperatures in parts of the Arctic, including Iceland and northern Canada, below average temperatures over northern Africa, southern Eurasia. It tends to be also wetter than average over northern Europe, but drier to the south near the Mediterranean region, also wetter than average over parts of the southern US. And in the negative phase, again, it's just the opposite. So we have above average sea level pressure over the North Atlantic, below average in the belt to the south. Tends to be cooler than average over northern Eurasia, as well as the eastern US, warmer than average over parts of the Arctic like Greenland. And then it also tends to be wetter than average in the Mediterranean region, drier over to the north. And these are just some of the basic temperature precipitation impacts. But again, the NAO is going to impact a large fraction of the climate system. It's going to impact ocean temperatures, ocean currents, marine ecosystems. It's going to impact on energy, wind energy, and agriculture. So you name it. So a lot of factors that are societally relevant are going to be impacted by the NAO. Okay, so now let's move on to the PNA. So first of all, what is the PNA? So the PNA is the second leading northern hemisphere atmospheric teleconnection pattern in winter. So again, the NAO tends to be the first, explains a little bit more variance than the PNA, but the PNA is the second leading pattern. It's also present throughout the entire year, but it's strongest in wintertime. It's a quadrupole pattern in the height field that's with action centers near Hawaii, the Aleutian Islands, northwest North America, and the southeastern U.S. So it's this sort of Rossby wave train type pattern extending across the North Pacific and into North America. So just as with the NAO, we have two phases of the PNA. So here we are depicting the PNA in the positive phase. So again, the blue contours represent negative sea level pressure or geopotential height anomalies. The red, positive sea level pressure or geopotential height anomalies. So in the positive phase of the PNA, we tend to have above average heights near Hawaii, and then a big area over the North Pacific with below average heights or sea level pressure. So this indicates a strengthened Aleutian low, above average heights over western North America, below average heights over the southeastern U.S. And again, this positive PNA pattern is going to be superimposed on the climatological geopotential height pattern. And so when we add the anomalies to the climatology, we see patterns that look like this. So in the negative phase of the PNA now, so that's opposite to what we just discussed, we could see that there's a reduction in the gradient over the North Pacific. And there actually tends to be a little bit more blocking over the North Pacific as well. Whereas during the positive phase of the PNA, you see the stronger Aleutian low, this strengthened gradient. So the jet tends to be stronger and more extended eastward into the Pacific. We see an amplification of the ridge over western North America and a deeper trough over the eastern North America. So this is showing the seasonal evolution of the PNA. Again, this is taken from the NOAA Climate Prediction Center website. As I mentioned, we have the PNA is strongest in the winter, so we see the most mature, strongest pattern in January. Well-defined quadrupole wave train type pattern over the Pacific North America region. In April, it tends to weaken, and then it's very weak in the summertime. And as with the NAO, the northernmost anomaly center tends to stay a similar location, whereas the belt in the mid latitudes tends to migrate a bit northward in the warmer months. And then you can see it still maintains this quadrupole wave train type pattern, but it's less well defined in some of these other seasons than in the wintertime. So how do we define the PNA pattern and its corresponding time series? So in this pioneering work by Wallace and Gutzler in 1981, they had a very simple definition of the PNA index as a weighted sum of the normalized height anomalies of the 4 PNA action centers. So they chose 4 different grid points, and you just take the average over those grid points with the appropriate sign based on the sign of the anomaly of the PNA in the positive phase. So the key strength of this simple index is it's the same as with the station-based NAO index. It's simple to construct and easy to understand. And again, it's likely to be highly correlated with some of the more sophisticated ways to define the PNA index. The disadvantages, same as with the station-based NAO index. We only have 4 fixed locations. So it doesn't allow the evolution of the PNA spatial pattern across different time scales. And we do see, as we saw in the previous slide, we see an evolution throughout the calendar year. But there's also changes in the pattern with response to these other time scales from interseasonal to seasonal to multi-decadal. And again, we have more noise from short-term weather variability when you only consider fixed locations that don't necessarily reflect the lower frequency and the larger spatial scales of these large-scale teleconnection patterns like the PNA. And so the NOAA Climate Prediction Center, they define the PNA pattern and the index in the same way I just described for the NAO index. So they do the same rotated EOF analysis that produces the NAO pattern and index time series. It also, emerging from this method, you get the PNA pattern and time series. But the PNA, again, in the wintertime, it tends to emerge as the second leading rotated EOF analysis behind the NAO pattern. And then it tends to be higher order in some of the other seasons. Again, it's a weak pattern in the summertime, but it's still present. And so here it's showing the PNA pattern from the CPC, and this is showing the time series. Again, you see a lot of interseasonal, interannual, and interdecadal variability of the PNA, as with many other teleconnection patterns. So these are the winter impacts of the PNA in the positive phase. So again, if you look at the sea level pressure field, among the 4 action centers, this Aleutian low anomaly is what really stands out. So we have a really strong Aleutian low. And associated with this strengthened Aleutian low, you see warmer than average temperatures over most of northern North America, below average over the southern U.S. near the Gulf Coast. Also tends to be wetter than average over the southern tier of the U.S., but drier than average over this large portion of the eastern U.S. and also parts of the Pacific Northwest. And again, negative phase, just the opposite of what you see here. So we have anomalous high pressure over the North Pacific, more frequent blocking over the North Pacific, cooler conditions over the western North America, northwestern North America, warmer to the south. Storms tend to be deflected more to the north, so wetter over the Pacific Northwest and parts of the eastern U.S., but drier to the south as a reflection of this change in the storm track. Okay, so now we're going to talk about which processes give rise to the NAO and PNA, and also how predictable these two patterns are. Let's turn back to the NAO. So the NAO tends to arise as the remnants of breaking Rossby waves over the North Atlantic region. So Rossby waves tend to travel along the jets, which serve as waveguides. But in the jet exit regions, the meridional PV gradient diminishes and these Rossby waves break. And this Rossby wave breaking is characterized by reversal of the meridional potential vorticity gradient. And so that's what I kind of depicted here in this schematic of wave breaking, these contours representing PV, and you can see this area where the gradient is reversed. And there are generally 2 types of wave breaking, anticyclonic and cyclonic. And so it turns out that this anticyclonic wave breaking tends to lead to the positive phase of the NAO, and usually there are multiple wave breaking events, precursor events to the west, and then wave breaking events over the North Atlantic themselves. And accompanying this wave breaking, we see cold advection to the north, and then warm advection to the south, and this leads to that low over high dipole that characterizes the positive phase of the NAO. The negative phase of the NAO tends to be associated with cyclonic wave breaking over the North Atlantic region. And associated with the cyclonic wave breaking, we have warm advection to the north, cold advection to the south, resulting in this high over low dipole characterizing the negative phase of the NAO. And whether these waves break cyclonically or anticyclonically often is determined by whether these disturbances are on the anticyclonic or cyclonic shear sides of the jet. And I don't really want to get into all these details of the dynamics, which can be complicated. But one of the key points here, these are processes that can be internal to the atmosphere. And so the time scale associated with these processes and ultimately with the NAO is oftentimes not much longer than the synoptic time scale. So the intrinsic time scale of the NAO tends to be on the order of about 10 days. And so that has implications for understanding the predictability of the NAO as well. Now the PNA, on the other hand, it often arises from the linear dispersion of a convectively forced Rossby wave. So for example, we may have enhanced convection over the central equatorial Pacific. So we have convective heating. And in the presence of westerly background flow, this can serve as a Rossby wave forcing. And so what we see is that the energy disperses poleward and eastward in this westerly flow. And this is the initiation of a Rossby wave train that often projects onto this PNA pattern. So this would be a depiction of the PNA, the positive phase, forced by this convective heating in the central equatorial Pacific. And usually the PNA development is not quite this simple. There's interactions between the convectively forced Rossby wave and the mean flow. So there's amplification through feedbacks between the PNA and the mean flow. So the Rossby wave breaking process that I talked about for the NAO also can be important for sustaining the PNA. Also, what's tends to be important for the PNA is the extraction of energy from the mean flow. So just outside the jet exit region of this East Asia Pacific jet, we tend to get barotropic conversion of energy from the mean flow into the PNA disturbance. But we also see baroclinic conversion of energy associated with the background temperature gradients. So again, it tends to be more complicated, and the PNA isn't always triggered by convection in the tropical Pacific. So it can develop in the absence of convection and through these processes that are really intrinsic to the mid latitudes. But the processes that are more intrinsic to the mid latitudes, they tend to be again occurring on these shorter synoptic and slightly longer than synoptic time scales. But the convective heating from the tropics, they can be associated with processes that occur over longer time scales. And so that can be a source of predictability for these longer subseasonal to seasonal and even decadal, multi-decadal time scales. So both the NAO and the PNA have intrinsic time scales on the order of 10 days. So that means they tend to grow and decay on these intraseasonal time scales. So here I'm just showing an example of the PNA and the NAO index time series over a recent segment downloaded from the NOAA Climate Prediction Center website. So on the top, we see the PNA index and observations, and also these, and the red lines are ensemble forecasts from the Jeff's forecast system. And what we see is that if you look at a given month, you tend to see fluctuations, from positive to negative values. So on the order of 2 weeks or so, the PNA index bounces up and down. And if you look at the NAO index, we see something very similar. So it tends to have fluctuations on the order of a couple weeks or a month. So if we have a positive phase dominating for 1 month, it doesn't mean it's going to prevail in the next month. We might just suddenly flip to negative phase. So again, this is just reflecting the intraseasonal time scale of these two patterns, and that does suggest that there are limits on the predictability on these lower frequencies. So, as I just discussed, the importance of internal atmospheric processes and the approximate 10-day time scale of the PNA and NAO suggest deterministic forecast skills can be limited to the weather time scales. However, there are significant ties to more slowly varying components of the climate system, which can provide probabilistic skill on these subseasonal to seasonal time scales. And so this is still a very active area of research. I think over the last, let's say, decade or so, really been a lot of investment into understanding the subseasonal to seasonal predictability and prediction of these large-scale atmospheric teleconnections, including the PNA and the NAO, and of course, the resulting impacts that on surface climate, including temperature, precipitation, wind, etc., that have direct impacts on us. And a lot of effort has gone into trying to bridge the predictability gap, the prediction timescales going from the short weather timescales to the seasonal timescales, and in that gap, in that week 2 to week 3, week 4 time frame, trying to understand, can we produce actionable forecasts on that subseasonal timescale? And so, if we can, then we should bet that both the NAO and the PNA are going to be important factors in being able to do so. So when we talk about the subseasonal to seasonal predictability of the NAO and PNA, we can expect that the excitation of Rossby waves by tropical convection will be an important source of this subseasonal to seasonal predictability. So the slow variation of tropical convective forcing provides these opportunities for forecast skill beyond about 2 weeks. So on the subseasonal time scale, the dominant source of this predictability related to the convective excitation of Rossby waves is through the Madden-Julian oscillation, or MJO. And I know you're expected to learn more about the MJO later in the course, so I won't go into detail, but I'll just do a brief introduction, and perhaps this will be a motivator for why the MJO is important to know. So the MJO is the dominant mode of tropical intraseasonal variability, and it's characterized by anomalous convection that propagates eastward across the tropics with a nominal time scale of about 30 to 60 days. And so typically we subdivide the MJO life cycle into these 8 phases that were defined by Wheeler and Hendon in 2004, with a nominal transition time of about 4 to 8 days per phase. So on the left here, I'm illustrating the MJO life cycle subdivided into these 8 phases. And in here, showing anomalies of rainfall. So the greens and blues correspond to above average rainfall. The browns represent below average rainfall. So you can see this east-west dipolar pattern in the MJO. So in phase 2, we see enhanced rainfall, enhanced convection in the western Indian Ocean, and suppressed convection to the east over the region around Indonesia and parts of the western Pacific. And so this area of enhanced and suppressed convection slowly propagates eastward through phases 3, 4, 5 until the convection, anomalous convection, propagates through the Indian Ocean, over the maritime continent, east of the maritime continent, into the central equatorial Pacific. And then the convection anomalies tend to die down as we move towards the eastern Pacific, where the sea surface temperatures are notably colder. But the circulation anomalies in the tropical atmosphere tend to persist even farther eastward. And the MJO itself can be skillfully predicted more than 3 weeks in advance by our state-of-the-art dynamical prediction systems. So this is a source of predictability for both the convection and the tropical circulation anomalies, as well as the response to the convection and the extratropics. So it's a key trigger of Rossby waves and many of the dominant global teleconnection patterns, including the NAO and the PNA. So I was a contributor to this study led by Emily Riddle in 2013 that demonstrated how the MJO may be an important source of subseasonal PNA predictability. And so what we did in this study is we calculated cluster patterns of 500 millibar height anomalies from the winter atmospheric circulation over the Pacific North America region. So when you do this cluster analysis, it's somewhat similar to the rotated EOF analysis in that you obtain these dominant patterns that represent many of the dominant teleconnection patterns that we know. And then we obtained 7 different 500 millibar height cluster patterns. And 2 of these 7 patterns clearly represent PNA patterns. So there's one cluster that resembles the positive phase of the PNA. So you can see the typical positive PNA wave train over the Pacific North America region with that strengthened dilution low, the ridge over the Western North America, the trough over Eastern U.S., etc. And then also accompanying this negative NAO-like pattern over the North Atlantic. And then we also had a negative PNA-like cluster, which featured this anomalous high over the North Pacific and then the trough over Western North America and the ridge over the eastern U.S. And so among these two PNA-like clusters, they accounted for about 35% of all the weekly 500 millibar height anomaly fields that we clustered. So if we look at this PNA positive cluster, what I'm showing down below on the x-axis, this represents the days after a particular MJO phase, and the y-axis represents the anomalous cluster frequency in terms of percentage. So a value of 100% means that the cluster pattern occurs twice as often as in climatology. And these are the anomalous frequencies corresponding to MJO's phases 5 and 6. And what we can see is that we have MJO phase 5, where we have anomalous convection around the maritime continent and points eastward. We could see about 25 days later, we have a significant enhanced frequency of this positive PNA cluster. And for MJO phase 6, where the convection shifts a bit farther to the east, it's about 5 to 15 to 20 days we see this enhanced occurrence of this positive PNA cluster. So that indicates that this positive PNA is more frequent about 10 to 25 days after the MJO is in phases 5 and 6. Now for this negative PNA cluster, we see it's more closely corresponding to MJO phases 2 and 3. So MJO phase 2, we have this enhanced convection in the tropical Indian Ocean, suppressed convection to the east near the maritime continent in the western Indo-Pacific. And about 10, 15 days after MJO phase 2, we see this significant enhanced frequency of the negative PNA cluster. And for phase 3, the convection has shifted a bit farther to the east, and we see about 5 to 15 days an enhanced frequency of occurrence. So this is an indication that the negative PNA is more frequent about 5 to 20 days after MJO phases 2 and 3. So this is extending clearly beyond this typical weather time scale of predictability of more than the 7 to 10 days that we see from our deterministic forecasts. And this doesn't mean that every time we get an MJO phase 2, phase 3, we can expect the negative PNA 2 to 3 weeks later. It's more of in a probabilistic sense. The probability of occurrence of this pattern is increased. And same for the positive PNA corresponding to MJO phases 5 and 6. So back in my later days as a graduate student, there were these two studies that came out that indicated that there's a stronger connection between the MJO and the NAO than previously recognized. So I think the connection to the PNA is a little bit more intuitive because the PNA is more closely connected to the tropical convective forcing in the Pacific. But the MJO also has a significant influence on the MJO over the North Atlantic. And again, I'm going to take an example from this Riddle et al. Study where one of the clusters we identified is this negative NAO cluster. So you can see the anomalously positive heights over the North Atlantic, Greenland area, negative heights to the south. And again, we're looking at MJO phases 6 and 7. So MJO phase 6, we have enhanced convection in the western and central equatorial Pacific. Phase 7 is shifted a bit farther toward the date line. And about almost 20 to 30 days after MJO is in phase 6, we see this enhanced occurrence of this negative NAO cluster. And about 5 to 20 days after MJO phase 7. So the negative NAO tends to be more frequent 5 to 30 days after this MJO phases 6 and 7. So again, MJO providing this probabilistic source of predictability for the NAO. And then another source of predictability for the NAO is rooted in the stratosphere. So stratosphere-troposphere coupling may be a source of winter NAO or AO predictability over time scales of several weeks. And this is particularly true and particularly a source of focus when we have the reversal of polar stratospheric winds that accompany so-called sudden stratospheric warmings. And this reversal of stratospheric winds may progress downward through the stratosphere and eventually into the troposphere, projecting onto the negative phase of the NAO or AO. And this schematic to the left, this illustrates the process. So in the wintertime, the polar vortex in the stratosphere, we have winds blowing from west to east. And under the right conditions, if we have tropospheric planetary waves that propagate northward, they may break in the stratosphere, transferring heat and momentum. We get this warming and this deceleration of the winds, and then the continued propagation of planetary waves. They will continue to break, but now they're going to break at a lower level. So that the warming and the deceleration occurs at a lower level. So we see this gradual downward progression of these polar stratospheric wind anomalies and temperature anomalies. And eventually, once these anomalies descend to the tropopause, sometimes they also descend into the troposphere. So it's not a purely deterministic occurrence, but we see under the right conditions, the anomalies will propagate into the troposphere and will project onto this negative phase of the NAO or the AO. Here's an illustration of a sun stratospheric warming. So this was from the 2022-23 winter. This is showing the temperature of the polar vortex. In the stratosphere, you could see this cooling in the winter. So we had very cold, near record cold temperatures during this winter. And then all of a sudden, and the warming that occurs is very dramatic. So over the course of several weeks, we see an increase of about 50 degrees Celsius, and sometimes the warming can be even more dramatic, at least over shorter intervals of time. So we're going from near record cold to near record warm over the course of several weeks. And this vortex, which is strong and stable at the outset, starts to become disrupted by the upward propagation, these planetary waves that break and warm, and eventually. Sometimes these anomalies again propagate downward until they affect the troposphere, resulting in the blocking that tends to occur over the North Atlantic and the accompanying temperature, storm track, etc. The anomalies that have a significant impact on the climate over the Northern Hemisphere. So these are the typical temperature anomalies that follow the sudden stratospheric warmings. So you can see cold conditions, particularly over Eurasia, warmer to the south, warm basically to the west of Greenland, cold over the southeastern U.S. And you may recognize these anomalies closely resemble the temperature anomalies we see with the negative phase of the NAO and the AO. So that's reflecting this change in the Arctic and North Atlantic circulation. And I think this is a classic figure from Baldwin and Dunkert in 2001 that illustrates this effect. So this is showing the phase of the AO, where warm colors represent the negative phase of the AO at different pressure levels from the stratosphere down into the troposphere. And then the x-axis, these are lags with respect to the negative phase of the AO, with lag 0 being the time of negative AO occurrence in the stratosphere. And a couple of key features from this plot, these sometimes referred to as these paint drip plots. So you can see this general downward propagation of the negative phase of the AO through the stratosphere that I just talked about. And then once it descends to the tropopause, we see these occurrences of the negative AO in the troposphere. So it frequently persists in the troposphere for several weeks. And notice that it's not continuous, so it's almost like there are pulses of this negative AO or negative NAO phase in the troposphere. And so, again, it's not deterministic. It's not like every time this happens, we get a negative NAO or a negative AO, but more frequently than not, we tend to see a negative phase of the NAO than the positive phase, and this can last for several weeks, which means that it is a source of predictability on these subseasonal timescales, and even extending to the seasonal timescale at times. So back in 2017, a team led by my postdoc, Jiaxin Black, tried to incorporate all these lessons we've learned about predictability sources for the NAO, PNA, AO, and then try to put it to the test by developing prediction models for these teleconnection patterns. So these were statistics-based predictions using our known predictors, including tropical convection, the state of the stratosphere, as well as the initial tropospheric conditions. And I won't go into all the details, but here's one of the results showing the prediction skill from our statistical models for both the PNA and the NAO. So on the x-axis, this is for the lead time, weeks 1 to 2, weeks 2 to 3, weeks 3 to 4, weeks 4 to 5. And the y-axis is the correlation skill, the PNA on the top, NAO on the bottom. And the orange line here represents the skill from a dynamical model, the CFS. And then the blue and the green line is for the statistical models that we developed. And then two key points here. So first of all, we have significant prediction skill for all the lead times we consider for weeks 1 through 5. And then the second point is that if we look at compare the dynamical model, the CFS, versus the statistical model, the statistical model becomes competitive with the dynamical model for weeks 3 and 4 and 4 and 5. So for these longer lead times beyond the 2 weeks, it seems like we are able to capture the dominant sources of predictability and incorporate this into a skillful prediction model for both the PNA and the NAO. So now we're going to move to seasonal prediction of the PNA and the NAO. And when it comes to seasonal prediction, the El Nino Southern Oscillation, or ENSO, is the dominant source of seasonal predictability, including for large-scale teleconnection patterns, and especially for the PNA. So the atmospheric convection anomalies accompanying the tropical Pacific sea surface temperature anomalies excite the Rossby waves that project onto these dominant teleconnection patterns in a similar way as it does for the MJO. So for example, when we have an El Nino, we have warmer than average sea surface temperatures in the eastern equatorial Pacific. These warm sea surface temperatures lead to enhanced convection over the central equatorial Pacific, suppressed convection over Indonesia. The enhanced convection in the central equatorial Pacific excites this Rossby wave train-like pattern that leads to this PNA-like pattern, which again impacts the temperature, precipitation, storm track, and has the classic impacts over North America, as well as potentially some impacts over farther downstream over the Atlantic and Europe. So these are the composite 500 hectopascal height anomalies for ENSO winters, and as I mentioned, for El Nino we have enhanced sea surface temperatures in the eastern to central equatorial Pacific. And if we look at the height pattern, we see that deepened Aleutian low. We see the positive height anomalies over North America, although they do extend farther eastward than for the classic PNA. And then we also have the below average heights over the southeastern U.S., a little bit more zonally elongated than for the classic PNA. So it's doesn't resemble the classic PNA pattern. And so back again when I was a graduate student, there were some papers that were debating, does ENSO excite the PNA or not, or these separate patterns? I would say that there's if we consider the PNA as a continuum of patterns, ENSO excites one member of the continuum. So it's a pattern that clearly projects onto the PNA, but there are other PNA-like patterns that may look a bit different. And then for La Nina, it's the opposite. So we have the cooler than average sea surface temperature anomalies. We have the above average heights over the North Pacific, below average heights over Western North America. So this clearly projects onto the negative phase of the PNA. So the boreal winter ENSO teleconnection projects onto the positive PNA during El Nino and negative PNA during La Nina. We can see a modest projection onto the NAO pattern as well. So especially for La Nina, you can see this negative NAO-like pattern. And so there's debate about how strong a connection there is between ENSO and the NAO, and there may be some variation within the season, some perhaps a stronger connection later in the winter than early winter. So ENSO drives the seasonal predictability of the PNA, and I think this is clearly shown by the study O'Reilly et al. 2017. So first of all, this is showing multi-decadal variability of the winter PNA and NAO prediction skill in an ECMWF prediction system. So it shows that the skill is not constant across time. This is going back to before 1920 and extending to near the present time. And you can see the PNA prediction skill is shown in red. The NAO correlation skill is shown in blue. And over the course of decades, the PNA skill has been, in some epochs higher than 0.6. Then you can see a decline in the mid 20th century before it increased again. The NAO skill on average is considerably lower, but it also shows a decline in the middle of the 20th century and then increasing. So on average, the PNA correlation skill is around 0.5, the NAO correlation skill around 0.3 in this particular system. But again, there's considerable interdecadal variability in this skill. And to show how the PNA prediction skill is clearly connected to ENSO, I think this figure from O'Reilly et al. Really drives home the point. So first of all, what do we see? So the red curve is what we saw before. This is the correlation between the observed and predicted PNA. So you can see the interdecadal variability where it's high early in the 20th century, then drops, and then it increases again later in the 20th century. And so this green line is the correlation between the observed PNA and ENSO. And ENSO here defined by the Nino 3 sea surface temperatures in the equatorial Pacific, so the Nino 3 index. And you can see there's almost a perfect correspondence between this correlation between the observed and predicted PNA and the correlation between the observed PNA and ENSO. And then finally, this curve in orange shows the correlation between the predicted PNA and ENSO. And so what it's saying is that, the predicted PNA, this is an ensemble average. So individual ensemble members will be different, but when you take an ensemble mean, there's a very close correspondence between the predicted PNA and the predicted ENSO. And so this decline in skill in the middle of the 20th century is associated with the decline in skill between, or the decline in the relationship between the observed PNA and ENSO. And so this may be an effect of just the variability of ENSO diminishing, and when the variability of ENSO diminishes, then you're losing that signal on the seasonal time scale, and your correlation is expected to drop. And as I showed earlier, so the NAO seasonal prediction skill tends to be considerably lower than that of the PNA. So the NAO, again, not as directly connected to the convection associated with ENSO. And so throughout my graduate student years and early career postgraduate years, that was, I think, the conventional thought that you have more skill in the PNA due to the direct connection to the convection associated with ENSO, and less seasonal prediction skill of the NAO because it isn't as closely tied to the slowly varying sea surface temperatures in the Pacific, and it's more tied to these processes that are internal to the atmosphere, so basically chaotic weather noise, which is not going to be predictable on the seasonal time scale. But over the past decade or so, there's been some research that suggests that maybe the NAO is more seasonally predictable than once thought. So some prediction systems show as much NAO seasonal prediction skill as that of the PNA, And a lot of these studies have been coming out of the Met Office in the UK. So I'll show a few studies here on the left. And this is showing a figure from one of the original papers, Scaife et al. 2014, showing both the observed winter NAO index in black, and then the predicted winter NAO index in orange from the GLOW-C5 prediction system, again out of the Met Office. And you can see a pretty good correspondence where the correlation skill is 0.62. Again, that's competitive with the sort of skill we see for the seasonal PNA index and that ENSO connection. So this was rather surprising. And I think we're still trying to understand what are the potential predictability sources that the model is capturing. So we know ENSO is one of them. There seems to be potential connection to the Atlantic sea surface temperatures. I mentioned the stratospheric polar vortex strength. That seems to be a potentially important contributor here. And other stratospheric variability, perhaps tied to the quasi-biennial oscillation. That's variability, more slow variations in the tropical stratosphere, which we'll get into here, as well as Arctic sea ice, particularly anomalies in the Kara Sea. So that's an area that's also received a lot of study and focus and potential connection to the NAO. That's not, I'd say, entirely conclusive at this point, but it's been an active area of research. But another important characteristic of these NAO predictions is what's been termed a signal-to-noise paradox. And so the NAO forecast signal is much weaker than we would expect given the high correlation skill. So I'm showing here a correlation skill of around 0.62. Given a correlation skill like that, you expect that the ensemble mean NAO index from the dynamical prediction model is going to have maybe 35 to 40% of the variance of the observed NAO. But it turns out the forecast ensemble mean variance is much smaller than that amount. And so the signal appears to be suppressed for some reason. And as far as I'm aware, there's not yet a satisfactory explanation for why that is. But if this holds out and turns out to be a true feature or true deficiency of our dynamical prediction systems, it has many implications, not just for the subseasonal to seasonal prediction of the NAO, but also if their models are not responding strongly enough to some sort of forcing, it could have important implications for regional climate variability, regional climate change. So this is, I think, another active area of research. So it just goes to show that there's still a lot of unanswered questions about our dominant teleconnection patterns, both the NAO and the PNA, predictability, the variability, the mechanisms. So it remains an exciting area of research. Okay, so finally, just some closing thoughts. So to summarize, the NAO and PNA are the two dominant northern hemisphere atmospheric teleconnection patterns, particularly in winter. So as we discussed, the NAO is a dipole of atmospheric mass fluctuations over the North Atlantic with large hemispheric impacts, especially over Eurasia. And the PNA is a quadrupole Rossby wave train pattern with greatest impacts over North America. And finally, atmospheric teleconnection patterns like the NAO and PNA have intrinsic timescales on the order of 10 days, but they also exhibit potentially predictable lower frequency variations on subseasonal to seasonal and even decadal timescales, owing to slower variations in tropical convection patterns, stratospheric variability, and possibly the cryosphere as well. So thank you for your attention. I hope you've learned something from this lecture, and it was a pleasure to produce it and to deliver it to all of you. So I wish you the best of luck in the rest of this course. Thank you.